It's a pleasure for me to introduce our plenary speaker this morning. It's Professor Xing Li. He is from the Robotics Institute from the Hong Kong University of Science and Technology, and he will give the talk on it's from geometry to startups. This listen a little bit strange. Everyone is eager what it is, but I think he will give a very interesting talk. How theory, a good model is useful to set up new application and to build a robust robot application and to show that it works. Looking to his careers, he was long time in his education with computer science, with electrical engineering, but also mathematics and also economy is some area he has engaged in. He studied at the South Central University, then going to Carnegie Mellon, making his master in mathematics. He received his PhD from University of California in Berkeley, and then he did continue to work at Carnegie Mellon and at MIT in the AI lab, refining the theory and the application of robots. 1992 he went back to Hong Kong and started at the Department of Electronics and Computer Engineering at the University of Science and Technology, Hong Kong. Yes, he had on his career a lot of awards related to his excellent, outstanding work. Then he was strongly engaged in IEEE. He was chairman at the Shanghai conference. It was ICRA 2011. And then going to his, it's a long list I have here to report, but he has to give the talk, not me. His interest is closely to robotics with robot components like finger hands, like parallel robots, like trajectory planning, collision-free planning, also imaging, localizing workpieces, inspection of workpiece, and also he is studying flying robots, unmanned aerial vehicles, also navigation and control. I assume also some applications looking to your work you have already done. A lot of publications, 2 books, which are good as a curriculum for education, from my point of view. And then he started several companies. I don't list them. He is IEEE fellow. And then now I think I open the audience for you, for your talk, and then thank you very much. Please.
Dear colleagues and fellow students, it is a great pleasure to be here and to share some of my experience. And I believe that many of you got into the field of robotics through your direct experience with robots, either a robot in a factory floor, prototype robots in the labs, or even toy robots. However, when I was first exposed to robotics, I had none of those. It was sometime 1982, my senior year at CMU. The Robotics Institute was just founded, and a new course in robotics was offered. For some reason, I got into the course. But I got nothing out of it except only the notion of homogeneous transform. And I was pretty bad on hands-on stuff. So I could not associate any physical meaning or geometric picture with the concept. I almost gave up. Then, fortunately, the summer before I went to Berkeley, I took an intern in Mark Reber's leg lab. I saw the real robot, a hopping robot, and also wired a few breadboards. And then I went to Berkeley, still want to study control, not robotics. And my advisor, Professor Shankar Sastry, was about to set up the Berkeley robotics program. So he said, Zishan, you come from CMU, so you must be the most natural person to help me on the robotics program. So I volunteered myself to organize the graduate seminar on robotics. I invited Mark Kokowski, Nakamura to give seminars on multi-finger hands. I was quite impressed by the complex motion displayed by the hands. And also, I have my own pair of hands, so I can do some experiment with it. And it's difficult to describe the motion. So I read a few papers on screw theory, and I was confused. And then one day, Shankar brought me a paper by Roger Brackett on the famous product of exponential formula. There it displayed precisely and clearly the relation between infinitesimal motion and the finite motion, at least for an open chain manipulator. And later I read another paper, also from the Brackett group, by David Montana on kinematics of contact. Geometry was used beautifully to describe contact motions. And I fall in love with that. And that was the topic of my PhD thesis on the geometry of a multi-finger hand. And afterwards, I had a chance to set up my own program. So the first recipe I prescribed to my own students was a seminar on differentiable manifold and the Lie group theory. They all struggled, but later they all loved the thing. So today I'm going to share with you my experience on this, and also an opportunity to pay tribute to the many pioneers and the researchers whose work have laid the foundation of an important subject of robotics. So here is an outline of the talk. I will describe the evolution of geometric robotics, and then some of its applications, and then I will highlight a grand challenge. I feel it is now mature to use all the work we have built to attack this grand challenge, which is to automate production of C3 products. So the geometric robotics has two parts. One on the geometry. The other, the use of a geometric tool for the analysis of robotic problems. And of course, on the geometry side, there are Euclidean geometry and the non-Euclidean geometry. And the central piece of Euclidean geometry is the Euclidean space and its geometric properties. Euclid, in his Elements, postulated the property of Euclidean space. And Descartes, through introduction of a coordinates, allow us to identify points in the Euclidean space with n-tube of numbers, which we refer as Rn. And of course, Leibniz, Newton built calculus on Euclidean space. And 100 years later, Munch introduced the calculus to engineering community. And today we know that by simplification or approximation, we can formulate engineering problem as an optimization problem in Rn. And those are the masters of non-Euclidean geometry. Gauss formulated one and two-dimensional differentiable manifold, or we know as curves and a surface. Riemann generalized that to higher dimension, 3 and above. Surface Lie and Felix Klein introduced the Lie groups and the transformation groups. And the notation we use today is due to Hermann Weyl. S.S. Chen is a master in geometry, but his influence to the engineering program in Berkeley is equally impressive. Jerry Marsden built the bridge between the geometry community and the engineering community. And of course, the geometric robotics has its root in the classical screw theory. And that deals with the infinitesimal motion, finite motion of a mechanism under constraints. And Francis Rowley laid the foundation of kinematics He introduced the 6 lower pairs, which generate subgroup motions, and the rubber ball, the foundation for screw theory, and the Hunt, Batimer, Ross, those are the masters of kinematics and the mechanism design, and John V used the Lee group to study mechanism design. So those are probably, I can call the classical history. The modern history of geometric robotics was opened up by Roger Brackett by his famous formula, the product of exponential. And he also produced a group of outstanding students who become important contributors of the field, include Montana, Lon Carrick, Frank Puck. And Sastre studied the Berkeley group along the same tradition with Payton, myself, Rich Murray, and also Ima applying this to computer vision. And the work on manipulation is documented in these 2 books. So, and also Thomas Lazona Press introduced the C-space concept, and also the MIT group, Mason, Kenny, applying to various other problems of robotics. And also the Burdick group from Caltech and his students to snake robots, hyper-redundant robots. And also Martin Booth introduced the geometry to grasping force optimization and Tony non-holonomic hands. And also Vijay Kumar, from his wonderful work on flying robots, Lee group geometry is apparent in there. Kodachek, the grasp lab. And also those are the important contributors. So I will collect a few problems which are geometric in nature. In other words, without understanding the geometry underlying those problems, you will not be able to have a full understanding of those problems. Those will include rigid body motion, the kinematics and the dynamics control, and the open chain manipulators, the forward inverse kinematics, and the parallel mechanism, the synthesis of robotic hands, the how to model grasp, and the also force optimization kinematics of contact, and the also parallel mechanism, the synthesis, and the also design. Biomechanics, how do we model the joints of the shoulder, the eyeball movement in a very natural way? And also critical components in machine design, such as CV joints and also the parallel mechanism machine tool modules. And the non-holonomic motion planning, how do you manipulate a ball within the hand without dropping the object? How do you understand a falling cat reorient itself? And also, how do you understand parallel parking of a car, even with a number of trailers? So those are the non-holonomic motion planning problem, analysis, motion planning, etc. And also some problems apparently don't have that nature, but you can model them as geometric problems. For tolerance control, you need to give mathematically precise definition of tolerance notions and the algorithm for their verifications using vision, laser, all kinds of sensors. And the localization of a workpiece, they are either no symmetry, with symmetry, or partially machined workpieces. And also for collaborating robots, left-right hand system, which I call Quotient kinematics machines. Okay, the left-right hands may have not be identical. So how do you describe such a system? How do you specify the motion types of the left and right hands? How do you synthesize such a system under their calibration? And also now increasingly we use systems of robots for a Workcell. Many robotic systems are involved. And they also, how do we build the workspace model, offline programming, and the kinematics and the calibration, etc. So these are the problems. I will give a review walk you through the basic concept of geometric robotics. The main point is to identify the configuration space of the robotic problem with a manifold or Lie group, and then use the geometry of this space for their optimization. Okay. So recall if we have a function defined on the Euclidean space, and we want to minimize this, and we find critical points, use Hessians to decide if it is minimal or maximal, and to compute critical points, we have to compute directional derivative. And to compute the directional derivative, we have to use the properties of the Euclidean space. And here are some simple properties of the space. It has one single coordinate system to identify all points of this space, has a linear structure. But a manifold may not necessarily have all those desired properties. An example of that is a unit sphere. How do we represent points on the unit sphere? We use latitude and the longitude angles. We can do this except for the North Pole, South Pole, and the meridian line connecting those. Those are called singularities. Aside from the singularity, we have one-to-one correspondence between points on the sphere and the points on the coordinate plane. So to make up for the missing points, we introduce another coordinate system, and which also comes with its own singularity. For points other than the singularities, I will have coordinates relative to the red system and also coordinates relative to the yellow system. And we require the change of coordinates be smooth. So if we pile up all such coordinate systems until they are union of the coordinate system, make up the whole unit sphere, we have a differentiable structure. So a differentiable manifold is a unit sphere plus the differentiable structure. And the examples, the n-dimensional Euclidean space, the configuration space of a two-dimensional robots with revolute joints, and that of industry robots. A special example of a manifold is a Lie group. And we know in order to represent orientation of a rigid body, we use rotation matrices. And we found if we multiply two such matrices, we also get a rotation matrix. And when we take the inverse, we get another rotation matrix. So in other words, the set of rotation matrix forms a group, and the group operation is smooth relative to the differentiable structure of the set. And that is what is called a Lie group. Okay. Another example of a Lie group is the set of homogeneous transforms, or the special Euclidean group of R3. And the advantage of a Lie group is that you have a canonical coordinate system to use for your computation, given by the exponential map. So if you look at the group and they take the tangent space to the group at the identity, that is the Lie algebra. And that is how it looks like for those two examples. And then you take the exponential, and for those two exponential is rotation about the axis or screw motion about the particular axis. And if we have a subset of a group, and if that is also closed under the group operation, it is a subgroup. So rigid motion generated by rotation about a revolute joint is a subgroup, and so are the rigid motions generated by the 6 lower pairs. They all form subgroups. And using those geometric relations, it is very easy to see the forward kinematics of an open chain manipulator is given by the product of exponential. And using this formulation, you have a beautiful derivation of the Jacobian, the inverse kinematics, and even proof optimal workspace design of the Apple manipulator. And for the falling cat, we can model it as two rigid bodies coupled by ball joints. And the configuration space is then 2 copies of the rotation group. And the control input of a falling cat is the velocity of the upper body with respect to lower body. So if you use angular momentum conservation, you derive a nonlinear control system in its configuration space, and you can show it is controllable, and a falling cat is able to reorient itself. And if a subset of a group is not closed under group operation, but still smooth, it is a manifold, submanifold. And an example, 2-dimensional example of the rotation group is given by that of the universal joints. It's given by product of 2 exponential. And another example is the exponential of a 2-dimensional subspace. And that is the configuration space for your eyeball movement. And those 2 are quite different. And actually we found you can generalize that to SE3. You take any subspace of the Lie algebra. If they are closed under the triple bracket, then you could obtain an impressive list of spaces that models motion of a natural system, CV joint, eye movement, knee joint, shoulder joint, and even 5-axis machining. And if the manifold has a metric, then you can measure distance. This is called a Riemannian manifold, and you can define geodesic equations. And for the case of a single rigid body, using the kinetic energy, you can see the Newton-Euler equations are actually the geodesic equations. And this is coordinate independent. And utilize this fact, Frank Park derived the dynamics of open chain and a closed chain manipulator that is very efficient, geometric. You can factorize the mass matrix, and the design of a control algorithm follows naturally. And if you manipulate a grasping object with your 3 fingers, you have a grasp map taking the finger force to the object force. Finger force has to satisfy constraints, okay? The friction cone constraint. And Martin Booth showed that finger force lying in the friction cone constraints if and only if a certain matrix associated with the finger force is symmetric and a positive definite. And this space is actually a Riemannian manifold. And you can formulate the grasping force optimization problem as a optimization problem of a function defined on the Riemannian space. Actually, this function is convex. So you have a convex algorithm for its solution, which is very fast. And those are the references. And another example of a manifold is a homogeneous space. This is a little difficult to understand, but if you look at the case of a cylinder, let's say finite cylinder, you do the usual way to model its configuration space. You will see that the rotation about the axis of the cylinder will not change the cylinder. So it has a symmetry. And the way to systematically get rid of the symmetry is to take the quotient, which is again a manifold of dimension 6 minus dimension of the symmetry. And you can generalize that to an arbitrary Lie group with its subgroups. Okay. And what does that do to us? Well, if you look at the workpiece localization problem, and you can formulate that as a least square problem in SE3 if the workpiece does not have a symmetry. Okay. And if it has a symmetry, you simply replace it with all transformations ranging in the homogeneous space. You don't have to do anything additional. And the tolerance notions are all expressed graphically. They lead often to contradictory and imprecise interpretations. And sometimes the supplier and the customer get into fight. So the way to do this is to give a precisely mathematical definition of all those notions. And those are all possible cases of tolerance notions. And you will find they all involve displacement of symmetric features, and the configuration space of those features you can easily discover. So one example is the flatness of a particular surface. You can formulate the problem as a minimax problem in a homogeneous space. And then using relaxation methods, you can very fast having a solution for this problem. So those are the sets of problems, and how we use geometry to address those problems. And we have good algorithms for their solution. So the next step is, what do we do with these results? We need to, so this is some of the story. Myself get involved. So we built a controller to implement the Riemannian optimization algorithm. Then in another event, a company from Shenzhen imported expensive machinery, and he could not get his machine to work. So we brought a controller, retrofitted the controller, and the company also made a fortune. So from this experience, I do see some good opportunities, because in the 1990s, all electronic manufacturing gets migrated from United States and elsewhere to China. And now that is a tremendous industry with about 20 million workforces. And in the beginning, all machinery also gets imported. But after a while, the manufacturing process gets localized. So we need to develop machines that incorporate the new processes. And to do that, we need a controller to support this effort. Okay. But in order to commercialize the results, we still need two missing components. One is a university policy that supports this effort. We were fortunate that the former chairman of EECS from Berkeley was our VP R&D. So he established a very generous policy for us to do that. The other piece is we need a foothold in Shenzhen, which is the center of action of all manufacturing. And the HKUSD established such a platform for students, faculty to commercialize and also spin off their startups. So that is how Google Tech get started. And those are some of our products. And today it is the largest motion control company in China with more than 50% of the market share. And through the Google Tech experience, it allowed me to understand what kind of students do we really need, what kind of skills they have to obtain in order to be competitive in this innovative environment. And then I went back to recall myself. I thought that what I missed as an undergraduate student should be very important as well to the students. That is the experimental side, or the experimental robotics. So I happened to teach a course on robot design, a project course for competitions. And the students got into the course, and also to facilitate their prototyping process, they went to Shenzhen to buy components, to make PCBs, and also do all the prototypings. And the iteration speed is 10 times faster than what they do in Hong Kong. So a number of students come out to be entrepreneur. One of those is Frank Wang, and he took the course twice, and his favorite was a controller for a helicopter. And while pursuing his graduate study, he set up a company in Shenzhen, and they called DJI. And then now DJI today is the largest manufacturer of drones product, and also the gold sponsor of the conference. Now with more than 4,000 employees, and those are the various products, and lots of awards as well, and also recognition. And its revenue over the last 5 years grew by more than 700 times. So that is an impressive record for a hardware company, robotic company. For internet company, you can do that. And the DJI story also inspired a lot of students in my own lab. So another group want to start a robotics industry robot company called QKM. So you know the name where it come from. So when you talk about industry robots, there are established players like ABB, KUKA, Yaskawa, and Fanuc. So we did lots of market study, and we found that all those robot companies arise from automobile applications. And those are some of the nature of the Chinese automobile industry. And another industry in China, which is I call C3 industry, for all the manufacture of your iPhone, iPad, computer, consumer electronics. And around 70% of the global 3C products are manufactured in China. So this industry is 4 times bigger than the automobile industry in China, which is twice the size of the US automobile industry. And the number of robots used is only 1/10 that of the Chinese automobile industry. And the requirements are totally different. No company is ever able to provide a satisfactory solution. So that is the aim of QKM. And another student project, e-propulsion, they want to be the Tesla in the water. So this is a summary of some of the spin-offs from my lab recently. And so I look back to the place where I come from. So that is Hong Kong, Shenzhen, and Dongguan. Some of you may not be familiar with that. And this is a distribution of some of the companies. And VJ once come to here and he said, Zishan, this place has a name. It is called the Hollywood of makers. And that is indeed true. There are hundreds, thousands, if not millions of companies that can help you to do the design, do the prototyping, small batch, large batch manufacturing. And you can buy all kinds of components and also logistic companies. If you want to set up your own production, you can do that in a week. And if you are going to do this elsewhere, probably 6 months with a minimum. So this place supported, those startup companies. We spend lots of time to understand finally this place. And we felt that perhaps other startups, young entrepreneurs from our own community may also benefit if we do something, allow them to do this. So we decided to set up a robotic startup facility, and we like to open this to all starters from the community. And so that is how it is going to work. And then group comes into the place. We can connect them with all the component supplier, with the supply chains, which we qualified already, and even angel funds. So they go through all the processes of a step very fast. Okay. And this is the place. We have around 26,000 square meters available, which will be tripled in 2 years. And also for company to grow their team, they need trained students. So we established a robotics school. This year we admitted around 110 students, and will be increased to 300 in 2 years. So finally, with a few more minutes, I'd like to spend some time to discuss the grand challenge that we have after the automobile case. So this is the C3 industry. And all kinds of products from communication, computer, consumer electronics, and even automobiles are also become electrical. And 70% of all those products are manufactured in the neighborhood of where I come from. And those are the typical manufacturing processes, from the casing to the key components and to the final assembly. And unfortunately, if you go to the production floor, you will see, except for printed circuit boards and a few key components, most of them are still manual. And I have from here a video from ABC News of Foxconn.
93 million iPhones last year and 40 million iPads. And the only reason they didn't sell more is that they can't make them fast enough. But that relentless demand has raised uncomfortable questions about how these precious objects are made and how the people that make them are treated. A few weeks ago, the company invited me to witness its first ever third-party audit of its biggest Chinese supplier, Foxconn. They're working on top secret projects for Intel, Nintendo, Dell, and many others. How many steps are there?
Around 141.
141 steps. But it is time now to think different about Apple. Because here it is. This is where your iPhone was born, and these are the people who brought it to life. My name is Bill. Nice to meet you. I'm first struck by how young they are. Not 13 like some of the horror stories I'd heard, but 17, 18. No one looked over 30. I know many came from poor villages out in the countryside with the hope of making $2 an hour, but their haircuts prove that teen style lives everywhere. I was expecting more automated assembly, more robots, but the sleek machines that dazzle and inspire and change the lives of people 8 to 80 are mostly made by hand.
And the company Foxconn in China alone employed 1.6 million workers to do all those jobs. And of course, if you compare what is at Foxconn or in this industry today with the industry perhaps 80 years ago, as depicted in the movie by Chaplin, they are very identical.
Attention foreman. Trouble on bench 5. Check on the nut tightener. Nuts coming through loose on bench 5. Attention foreman.
Yeah, so you got to the point, right? You see that the whole industry today has not changed much from that of 80 years ago. And from the Chaplin movie, you also see workers are more or less treated like, animals or implied, right? So how do we make a change on this? And I believe that the change will take steps. And that is what is today. A typical line employs about 120 workers. And as you have seen in the ABC News, even for casing machining, they all break down into 140, 20-some steps. And slowly, this is going to be changed. And we are sure because of the high rise of labor, shortage of labor, half of the 200 million workers, okay, the whole, electronic manufacturing industry will probably disappear. So those will be replaced by robots, but not all at once. It will go step by step. So the next logical step is to replace some of the critical functions by robotic cells. And those robotic cells will work along with human workers. And as we acquire experience and build more and more robotic cells, we will have probably what we like to see, fully automated assembling and the production line for this industry. So to address this grand challenge, I believe that the work that has been accumulated in the whole robotics community for the last 30 years will play a critical role. And here is what our thoughts, how do we approach the problem. The first problem is the design of modular, flexible, cost-effective work cell. And the cost-effective And also modular means nature reflects the nature of the requirement. That involves a low degree of freedom, integrated robots, having compatible motion types, smart grippers, fixtures, parts feeders, sensing system, and also automatic generation of Workcell layout. In some industrialist words, automated automation. And the other thing is rapid deployment of the Workcell. For an automobile line, you have 1 year to set up your production. And for this industry, you have only 2 weeks. So rapid deployment is the key. And that will involve calibration, localization, environment mapping, offline programming, parameter optimization, inspection, diagnosis, and probably large data collected in this process can be utilized to continuously improve the production line. So that is where machine learning comes in. So I think I can conclude my talk with a few remarks. First, geometric robotics provides rigorous, precise, unifying tool for treating the diverse, complex behavior of various robotic systems. And through 30 years of development, this subject of robotics is now mature and also is ready to go. And the C3 manufacturing automation is the next grand challenge for the community. And I believe that geometric robotics will have a lot to do in this effort. And finally, for young students who are thinking to commercialize their research, finding a new path, believe that a rapid iteration, fast scaling up are two critical facts that determine the fate of their startups. And the Songsan Lake Robotic Startup Facility hope can contribute to the success of their effort. So that is all I have to say. Thank you.
So thank you very much, Professor Lee, for your very interesting talk. Maybe we have some remarks and questions from the audience. So, can you go to the microphone, please? There is one at
Thank you very much for one of the best keynotes I heard until today, for highlighting the role of geometric mathematics. However, I was astonished to hear that the first startup you started with was called Google, which is very close to a well-known company. And one of the robots that you demonstrated today, or you have shown in your slides today, is the Delta robot, which has been invented at the ETH in Zurich 30 years ago and been used in packing chocolate for many years. So despite all the mathematics, I think that some innovation is needed. And in my opinion, the determining factor for the future will be material science and not mathematics. Thank you.
Thank you.
Yeah, thanks for the comment.
So are there other questions, comments? I have a question. I think 2 weeks to set up a manufacturing cell is really very spotty. Do you have also some requirements to the product? I think the product must be optimized to manufacture it quickly if you want to set up it really in 2 weeks.
Yeah, I think this is why the calibration and of the whole thing is very important, and automatic doing that. Yeah.
So, additional question, remarks? Well,
so Professor Lee, so you're talking about the grand challenge, but in your talk you didn't talk about the solutions. Can you give us some hints how to solve the grand challenge? Thank you.
Yeah, I think I have highlighted some of our thoughts on how to address this grand challenge.
so if there is no additional question, and I want to thank you again very much for your very interesting presentation.